now move on to our third presentation of this session, and this is going to be presented by Dr. Jinlian, who is the Associate Professor at the Institute of Textile and Clothing at the Hong Kong Polytechnic University. Dr. Hu completed a PhD from UMIS in Manchester. She specializes in textile mechanics, smart materials, and image analysis. Recently, she was also awarded the Distinguished Achievement Award of the Fibre Society of the United States of America. The paper she's going to present today is the application of tensile drawing processing to rotor spun yarns, which is a result of a joint research between the Institute of Textile Clothing at the Hong Kong Polytechnic University and the University of New South Wales, Australia. So can I request Dr. Hu to make the presentation?
Thank you, Mr. Chairman, for your kind introduction. Good afternoon, ladies and gentlemen. It is a great pleasure for me to present a part of our work in front of you. As the Chairman introduced, the title of my presentation is The Application and Modeling of Tensile Drawing Processing to Rotor Spun Yarn. Actually, this slide is prepared by my students, and the majority of the work, particularly the modeling part, is done by my student, PhD student. She's not here today. My today's introduction includes the following sections: background, experimental, results analysis, theoretical modeling, and conclusions. The background of my presentation started with the introduction, the analysis of a rotor spinning system. This is a now very widely used system. It has the advantages of elimination of roving and the winding process. It has a phenomenal growth in productivity, and it has the capability of handling short length fiber or even wasted fibers. But this system has also the disadvantages. For example, it has a narrow range of yarn counts produced, usually from coarse to medium count. It has a limited diversity of fibers handled as compared with ring spun yarn, such as the cashmere wool. They cannot be processed, or they have a very bad performance with these kind of fibers. It has a very low, comparatively lower tenacity. It has a particularly harsh hand feeling of fabrics. We applied a so-called tensile drawing processing on this kind of improving the rotor spun yarns, particularly its handle feeling. The tensile drawing processing, many of you may have learned that it's applied to filament yarns, to filaments. The continuous development structure with increasing drawing ratio in terms of molecular orientation and increased crystallinity. This kind of process can enhance the properties of the filaments in yarn mortars and the breaking string. We applied this process to ring spun yarns before. We want to know whether this tensile drawing process can also enhance the yarn properties. The result of this trial is that it has too much hairiness, it has a deteriorated fabric performance, it has difficulty in downstream process. It has a decreased yarn elongation, reducing yarn in tenacity, even the collapse of the whole yarn structure. This is a lesson we learned, but we didn't give it up. We tried this method to rotor spun yarn. We applied two-zone rotor spun yarn Two-tone rotor spin yarn structure has the two-layer structures. The after wrap sheath may provide some cohesion in case of yarn structures collapse. More hairiness may facilitate the fabric handle, and you can improve fiber alignment so as to increase fiber extent or even yarn tenacity, as well as the appearance of rotor yarn fabrics. It can activate yarn spinning limit. That means we can draw a very coarse yarn into finer yarn that extend the spinning limit. So this experimental process is done like this. We have spinning, and then tensile drawing. We have yarn testing, fabric testing, scoring, and leading. Leading and fabric testing. These are the yarns we use for tensile drawing. The yarn counts, we have different yarn counts, we have different twist factor, and we apply different drawing ratio, as shown in this table. Here is a tensile drawing device. We have bobbin from the spinning system, and we have a feeder rotor, and then a drawing rotor. There is a speed difference between the drawing rotor and the feeding rotor. So the yarn is stretched, so it is tensile drawn. After we use the tensile drawing process, the yarn is tested. The yarn is tested in terms of yarn evenness, hairiness, tensile properties are also tested. We also tested the yarn diameter, yarn extension, yarn twist, and the yarn bending properties on the KES system. After the yarn is tested, after the yarn is drawn, we produce the knitted fabric to see the performance, to see the improvement of fabric appearance, fabric handle feeling, as well as its mechanical properties. All yarn samples, no matter with or without tensile drawing, are produced into knitted fabrics, since the preparation of all fabrics would involve too much time and labor. Because knitted fabrics is very easy. We only need one yarn. For woven fabrics, we have to prepare woven yarn and woven beads, so that's very time-consuming. We compare the fabrics made from yarns without and with tensile drawing to see the change of the properties. We also apply the scoring process to release the tension, the stress during the process. So, afterward, we tested the fabrics. This includes the fabric tensile, bending, and compression and shear properties, surface properties and the thickness on the KES system, fabric drape properties, abrasion and pilling property, shrinkage. We also apply the image analysis for some properties, air permeability and dyeing property. Here are the results of our test. The structural properties of yarns have changed. Okay, these are the trends of change of different properties. First of all, the yarn diameter. Yarn diameter has decreased. That means we can increase the count of the yarn. And the yarn twist level is decreased. The packing density is increased. Yarn evenness is increased. Yarn hairiness is increased. Yarn length is increased. Mechanical properties can change in this way. The yarn modulus is significantly increased. Tenacity is increased. Elongation decreased, and bending, rigidity, and hysteresis are increased. The yarn properties. This is the fabric properties. The fabric properties also change. Before, this is before the tensile drawing. This is after the tensile drawing. This is before, this is after. Actually, this indicates that the durability of the fabric is decreased. That means the fabric becomes different. Okay, we know the change. We have already experimentally know we can change the fabric property. Here the fabric property changes. Fabric thickness is increased. Fabric dimensional stability not influenced the band, not influenced, or it has very little change. And fabric fullness and smoothness is increased. Fabric hair mobility is increased. Fabric thread property, the durability is decreased. Fabric peeling property remains similar, and fabric harsh peeling is decreased. This is the most significant result. Fabric processing performance has been increased, has been improved, and the fabric luster is improved. It actually looks much shinier, much softer. So this is the result to the fabric performance and appearance. And after we made this kind of yarns, and we know the results, we know the change to the fabric properties and performance. We also did some theoretical analysis, theoretical modeling. We have some fundamental assumptions used in the modeling. First of all, we use the discrete fiber modeling principle. We use the energy method, and we use the Dr. Calave's surface path hypothesis. And here the other assumptions include changing pitch system, coaxial fiber genesis, non-uniform packing density, and we have the mass conservation during the tensile drawing process. No intersection between fiber genesis. The unit fiber length is considered a yarn model. So here the strategy we used. Suppose we know the yarn deformation and formulate a fiber strain energy, construct a cost-state equation for integration, and identify the boundary conditions. And then we can determine tension to specimen by calculating the partial differential differentiation. And the stress strain curve can be derived. Here is the Postle equation, and there's a Jiang region and Jiang region. We can identify the boundary conditions. This equation represents the this is the unjammed region, and the jammed region, they have the same radius. And these are the, and then after this we can calculate tension from the energy equation. We also, by calculating this tension stress strain curve, we have to have pitch function. Pitch function is made a tracer fiber image. We use nonlinear regression analysis to get the curve fitted. Here is the pitch distribution curve. We got a cubic function of corresponding radar position. Here is the stress strain curve we obtained. Control is not very convenient. What you see, actually the pink line represents experimental results. The green line represents the results we predicted by using changing pitch system. And this curve is obtained by assuming the pitch system is constant. We can see these two curves have a very good agreement. That means this the equation, including the changing pitch, has a better predictability. And by using the results, we can also analyze the fiber stream within the yarn in relation to its radial position. We can compare the fiber stream within yarn under different conditions. One is the constant pitch scheme, one is the changing pitch scheme system. You can see the fiber strain distribution is quite different. So basically, the fiber strain is smaller or identical in the changing pitch system. Here is the fiber strain in relation to the yarn strain. We can have different. We can get a series of results in relation to the radial position. Okay, here we come to the conclusions. Improve the tensile drawing system can improve yarn properties. For example, the reduction yarn diameter can increase the yarn count, increasing the resistance to physical deformation. That means the yarn smartness and bending stiffness. It can increase in the packing density for the general yarn, also the tenacity. Improvement in fabric properties include manually improve the inherent harsh hand feeling of open roller spin yarn fabrics, making the fabric cooler, thicker, and smoother. Improve the process performance. It has better luster and even whiter appearance. Here is the conclusion to our modeling, yarn modeling. We first of all use the original change pitch system. This can give the better agreement with experimental results. You can simplify complicated process by using any method. We can increase the accuracy of the predicted stress strain curve. We also use a new method to determine pitch function. We hope this model, this work can deepen understanding of Rotor spun yarn and help design yarn with desired properties, particularly during the tensile drawing process for Rotor spun yarn. That's the end of my presentation. Thank you very much for your attention.
Thank you, Dr. Liu. We have time for just one question. You please give your name.
Name.
Rotor spun yarn, the split of its rotor spun yarn, the split of its growing popularity suffered the disadvantage of lower tenacity, limited count range, and harsh hand feel of its end fabric. To eliminate these drawbacks, the what called tensile drawing processing was applied. In fact, it is the first one time for me to hear about such a process, tensile drawing process. Please show briefly how this process is achieved.
How this process is achieved? So you mean show you the tensile drawing process? You want to know the tensile drawing process? Yeah, we have a slide here. Yeah, here is the drawing process we apply. In fact, before this, we tried many methods. For example, we just put the yarn in a tensile drawing, in tensile testing equipment.
Is it a drawing stage?
This is our process applied. Actually, the yarns are wound many coils, and then we have this is the drawing roller, this is the feeding roller. Drawing roller has a much higher speed than the feeding roller. Is this clear? Because there's a velocity difference, and then the yarn is drawn.
Have you a paper about this?
Paper? Yeah, we have 3 papers coming out from the Textile Research Journal. We also have 2 patents for this process.
Thank you.
Okay. Thank you.